divergences here when this thing vanishes give rise to significant problems and errors, especially at these nodes. And so one has to look for a slightly better method, even if it's not precise, in order to do this job. And the way one can proceed is the following. So imagine we have, this is the measured critical current as a function of flux. So this is this absolute value of the Fourier transform of what we're interested in. And the fact that the nodes are lifted in this example indicates that there is both an even function of the current distribution and an odd function. Obviously, if there was no odd part, the Fourier transform is real. And if it's real, it could only acquire a plus or a minus sign, which means that the nodes, it always must cross zero. And so the nodes can't be lifted. For a symmetric current distribution, nodes can never be lifted. So in order to reconstruct both parts, the real and the imaginary part of the Fourier transform, one can basically do the following. Let's ignore for a minute the fact that the nodes are lifted. This would give us just the symmetric part of the distribution. And to construct it is very easy. We just take every second lobe and flip it. And the reason is that the phase can either be 0 or pi, so it could either be plus or minus, and that's the only solution for this kind of critical current. And this now gives us the symmetric part of the current distribution. Note that the symmetric contribution to this critical current at the nodes is 0. So when the nodes are lifted, this is a direct measure of the asymmetric part of the current distribution. And so we can take these values of these nodes and interpolate in between them. And it doesn't really matter so much how you interpolate between these values, and the reason is that the symmetric part shoots very drastically up. So we're assuming we have a current distribution that's mostly symmetric with some asymmetry. So it really doesn't matter whether you spline or you have a linear segments connecting these points, but you get the asymmetric part of the Fourier transform here. This is the imaginary part, the green curve, and now you can use both to extract the full current distribution. I'm going to basically show you results of this procedure taking advantage of both the symmetric and asymmetric parts of the current distribution. All right, a little bit of details about the samples. The samples are grown in MBE and they're complex. I want to point out that this quantum well that the electrons live in here, this yellow thing, is fairly narrow on the order of 8 nanometers. And in order to get good superconducting contacts, typically what we need to do is we need to etch down very precisely to the middle of this quantum well. If we're a little bit above or a little bit below, the quality of the superconducting contacts degrades significantly. We can then construct these kind of van der Plas structures or Hallbar structures. These are metal contacts. This is the material itself, and then we can have a metal gate sitting on top. These two DEGs are fairly high quality when the Fermi energy is in the conduction band. They have mobilities in the several 100,000. They're very nicely gateable. They show nice quantum Hall physics, and the splitting between the even and odd quantum Hall states appears at very, very low magnetic fields because these systems have a relatively large G factor. Density is very, very nicely tunable over a range of densities in these systems. So they're pretty well behaved. And so we go ahead and we construct a mesa, a structure that consists of this quantum well, which is this green block here. And these are these superconducting contacts, aluminum contacts that have been etched into the quantum well. And we can look at the current voltage characteristics. So this is the resistance as function of current bias, and you see a very nice supercurrent flowing in this system up to several hundred nanoamps, and then a sharp onset of resistance, some hysteresis that has to do with whether this junction is damped or not. Here's current voltage characteristic, again showing very nicely the critical current in this device, 0 voltage generated up to some several hundred nanoamps. And then we go ahead and we look at the Fraunhofer pattern. So now we're looking at this Josephson junction as a function of magnetic field, and we see a very nice Fraunhofer pattern where indeed the central lobe is twice as wide as any of the other lobes, and the magnitude of these lobes decay. Note that this is a little bit asymmetric. And the reason has to do with hysteresis in the way we scan the magnetic field. So there are some trapped fluxes that sit inside the superconductor that can lead to this kind of asymmetry. It is not of fundamental importance. And we can extract one important quantity from this measurement here, and that is the area of the device. And what we note, and the area is just one flux quantum, which is extracted from this magnetic field. And given that we know this dimension very, very well, this is just a lithographic dimension of where the electrons reside, we can extract the other dimension, and I've drawn the area that is extracted from this measurement here in blue. And you see that it's considerably larger than the area that you would expect, which is this little green rectangle. And the reason is that the magnetic field, as when it's applied to the system, is rejected by these superconducting contacts. And so part of the flux ends up funneling into the junction and part is rejected. And so the total amount of flux going into the junction is the original one, this little green rectangle, plus half of the flux applied to this contact and half of the one applied to this contact. So it all works out very, very nicely. And now we can add a methyl gate so we can explore how this Fraunhofer pattern evolves as we deplete the system and go into the topological regime. We can look in the normal state what the resistance is and see indeed that as we deplete the system it goes into this quantized Hall state, and the resistance is roughly 2e squared over h, as you would expect for a two-terminal geometry. And this is maybe a summary of what we expect. I'll show more details, but just a highlight of what the end result is. So this is what you've seen already at large density where current is flowing uniformly, and here now we're really inverting the Fraunhofer pattern for a current distribution. And you see that indeed it's a little bit asymmetric, but nonetheless current is very much flowing uniformly through the bulk of the structure. This is exactly what you'd expect when the chemical potential lies way well in the conduction band. Once we deplete, however, so now we're approaching this quantum spin Hall state, you see that the Fraunhofer pattern changes drastically. Note that here the width of the central lobe is twice the other lobes, and here the width is 1. And it has this kind of very slowly decaying Fraunhofer pattern. And if you now invert this, you can very clearly see that current is really centered along the boundaries. And the fact that you have this envelope here, you see that the envelope is not even monotonic, is the reason you get these kind of steps. The intrinsic structure of the edge is not something generic. It will be different between different structures, but nonetheless you see the power of this technique to reveal something that's really on the order of 100 nanometers or better in terms of determining where current is flowing in this device. So let me show just a little bit more details on the transition from the bulk to the edge. So what you see here are color maps of Fraunhofer patterns. Each one of these slices is at a particular density, starting from high density going to low density. What you notice mostly is that here again the central lobe is twice as wide as the other lobes, and the intensity is dying out. So if we want to see what happens normalizing to the maximum critical current, this is what you see here. You see indeed that the central lobe is diminishing and becoming a single phi naught lobe, and the weight of the side lobes becomes stronger and stronger relative to the peak. And this is the corresponding current distribution. You see that you start with a very nicely uniform current distribution, and then as you approach low densities, the current is really flowing only in the boundaries of the sample. And this is the range of resistances that one is seeing here. We're approaching all the way into the quantum spin Hall regime, and at the lowest density, these are the kind of widths that one extracts for this particular device. And now one can repeat it on many different devices. Here is another junction showing a very nice transition at a lower gate voltage from uniform to edge-like. The same characteristics starting with 2 phi naught going to 1. The reason I'm emphasizing the fact that you can just see the 2 phi naught going into 1 is that you don't really need to do this inverse Fourier method to realize that something very dramatic is happening to the current flow distribution. It's nice to be able to go through and get a nice image, but you don't really need to do it in order to realize that the current is flowing at the edge. In this particular device, the edge modes are very narrow, on the order of 200 nanometers. Here is yet a third device, smaller in the original width, so you see the separation between edge contact is small, and again, sub 200 nanometer edge currents in this device. I'm going to skip this slide. Now, perhaps the most... Yeah, no problem. Perhaps the most dramatic test of whether what we're seeing here is really due to the topological nature of this quantum well or not is to choose a quantum well for which we don't expect the existence of edge modes. So let's choose a quantum well whose width is below the critical dimension, below 6.3 nanometers. Here we're studying a 4.5 nanometer quantum well. And in that case, the system should be a normal insulator, should not show any edge modes. And indeed, you can see that within the entire range of densities, same resistances that we've scanned before, but within the entire range, the Fraunhofer pattern really is not changing, and the current distribution is also not changing. So nothing really is emerging at the edge, even though the magnitude of the critical current is diminishing. We are entering the gap. Critical current is going down, but nothing lives at the edge. So this is really a strong, in strong support of this kind of edge picture. Now I want to say maybe in the last few minutes of this talk something about these edge modes. So first of all, there is a real question of whether this kind of relation holds. If you think about these edge modes and you think about them being one wavelength, or basically a mode. In the interpretation of this kind of current phase relation, we've assumed that J of x is a classical current. But suppose you have a very narrow channel carrying current, these edge modes, and there's only one quantum mechanical state that lives there. What is really J of x? Is it just the current operator times psi squared, the probability density of the electrons along this edge? Is that the correct result? I think this is not correct. In fact, I think one really needs to develop a proper theory for when this is has a single mode or two modes or three modes, in order to really be able to say, oh yes, this is really the wave function of this mode at the edge. So this is one question that I'd like to pose. The other one is, what might give the variations in the width that we're seeing between different devices? And one interpretation that we have for that is that obviously the system is not ideal, and the width of these edge modes critically depend on where the chemical potential is sitting. As you bring the chemical potential closer to the conduction band or the valence band, these edge modes merge into the bulk. And so as long as there is a little bit of chemical potential fluctuations along the edge, this Fermi energy is sitting in different locations along the edge, and so the width here is varying as the electrons propagate from something that's very, very narrow. And theoretical calculations for this system predict that the edge mode in the middle of the gap should be on the range of 50 to 100 nanometers. But as I'm saying, our interpretation here, the way we interpret the result or analyze it, is to assume that this is really just, there is no dependence on the lateral coordinate. J is only a function of x. And of course, if J is really a little bit of function of y as well, then we're averaging over that. And that could also give rise to some deviations between different devices. Finally, I want to point out that we are seeing very, very often node lifting. And so far I've interpreted node lifting in terms of asymmetry in the current flow pattern. But what I'll do starting from the next lecture is to give you a different possible interpretation of node lifting that has to do with the true nature of these one-dimensional helical states coupled to superconductors. As I mentioned in the introduction, these helical states, when they're coupled to a superconductor, actually form topological superconductors. And they have different properties, current phase relations, than the one that I've talked about. And these might give rise to these kind of lifting of the nodes. Experimentally right now, we don't really know to distinguish between asymmetry and this kind of other interpretation, but at least I'd like to present theoretically, starting with the next lecture on Friday, what the role of topological superconductivity in this particular measurement is, and then go on to describe the effects of in-plane magnetic field and finite momentum pairing. So with this, I think I'll close today.
actually resolve that?
Yeah.
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 If it was really clean, you would have the resolution to do that.
Yeah. Yeah. I mean,
when you see 200 nanometers, that's not a resolution limit, that's way above it.
yes, that's right. So that's right. Our resolution limit is probably in the range of 10 nanometer or so. It really depends on the magnitude of the critical current. If we can go out to very large magnetic fields, this corresponds to very short wavelengths. So 50 nanometers is not too hard, but it really depends. If the magnitude of the supercurrent in a particular device is not high, we won't be able to go there, and then we'll be limited to a wider dimension. But typically, we can push this down to 10 nanometer or so. But there are intrinsic limitations that I was mentioning, and that is that the way we analyze the data is to assume that current is only a function of x. This is fundamentally incorrect. And so we can improve that by making the aspect ratio even larger, making the distance between contacts shorter. But nonetheless, I think that there is going to be something that has to do with improving the way we analyze the data, taking into account the fact that actually current paths are not just going along X. And I'll have a little bit of a flavor of that in the next lecture, talking about the effects of in-plane. You'll see that they're taking trajectories that are all trajectory going from any given point to any other given point here play a very important role, especially if the device is ballistic.
Is this lack of exact quantization of the current, that it's not quantized exactly to the square root of h, like a materials property? Do you expect that subsequently different materials will show exact quantization, or you think there'll always be some, like it's not going to sometimes asymptote to a really?
So I would say my answer would have two separate aspects to it. One is a theoretical one. I think, what are the mechanisms that can lead to resistance that's larger than the quantized resistance? This is something that's under debate and discussion right now, especially as a function of temperature. In the absence of interactions, for example, all models that I'm aware of all extrapolate towards the quantized value as you lower temperature, very different from what the experiment is showing. If you include interactions, I think there you might expect resistance going up, but I think observations are also, I don't know to say that they're consistent with what is seen. So I think that there's some piece of physics that we're missing in order to understand exactly the origin of what's going on. Now, from a practical standpoint, whether making better devices will show less of that missing piece of physics, very well so, could be the case. Just to point out right now, the physical location of these edge modes is a region that has undergone severe processing, chemical etching, exposed to air, exposed to solvents, exposed to polymers, and so on. So there's a lot of crap sitting there. It would be lovely if we can find a way to form a junction between a topological quantum well and a non-topological one that sits inside the crystal, that is not formed at the true boundary of the sample. Then I believe that we would have better quantization, less of this unwanted physics playing role.
So in your maps of current versus position, there are some spikes that are outside the sample area.
Right.
What's causing that effect?
Yeah, so that's an artifact of this inverse Fourier process, and sometimes it's more pronounced as you see it here. As you can see, these are harmonics, and so they're clearly artifact. They are sitting outside, and they to some extent limit our ability to extract quantitative measures on. So you can use them to say what are the error bars in what we extract, and in terms of the current flow patterns. And as you can see, the area underneath these kind of spikes is maybe on the order of 10-20%. So they're